Okay. The recording of the lecture for Tuesday, February 6th failed, and not discovered uh, until the end of class that it was had not been recording. So I think I was thrown off at when on a Mac, when the green light is on, um, that's when the webcam is active. It doesn't mean necessarily that it's recording. So apparently it wasn't really recording the whole time. I really thought I hit the button to start recording, but apparently I had not, or it hadn't registered. So there was no video. So what I'm going to do is try to recreate as much as possible, at least sure that the essential information is on video, so that everybody who could not be because they're remote would have access to the exact same information that everybody else does. So I have my notes from the class. I'll just do my best to recreate all that. So the subject, so it's not going to be as fun, sorry. Well, actually it might be, because I'm sure I'm going to be snarky because of what just happened. So the subject was section 3.3.1 in the textbook on banded systems of equations. So I'm going to illustrate with a example of a matrix A that is a banded matrix. That example was 8 by 8 matrix, and I'm just going to use X's to refer to non-zero entries. So then I'm not going to write out explicitly 0 for 0 entry. Often blank space will signify the 0. Here is entries on the main diagonal, and then I have these non-zero entries below the diagonal, and then above the diagonal as well. Okay. So then everything else in the matrix is 0. So all the non-zero entries are confined to this narrow band. So I get some terminology at you to discuss bandwidth. So I'm going to circle here the main diagonal. Okay. And I'm going to define the quantity, and sorry, I need to check in the book. I want to make sure I'm using the exact same notation as in the book. Okay. So I'm going to define P. Use P to refer to the upper bandwidth. And upper bandwidth is equal to the number of superdiagonals. I should say the number of non-zero superdiagonals. Okay. So in this case, so that's equal to 2 in this case because I have this diagonal, the immediate superdiagonal. So just to be clear, superdiagonals are above the main diagonal. Okay. So I have this superdiagonal and then one more above it. So 2 superdiagonals altogether that have non-zero entries. All others above that are. Sorry, I want to make sure absolutely sure I said the right thing. 2 diagonals have non-zero entries, and then all other superdiagonals above that are entirely 0. Okay, that's upper bandwidth. Q is the lower bandwidth. And that's equal to the number of non-zero subdiagonals. So, as the name suggests, more intuitively than superdiagonals, these are diagonals that are below the main diagonal. Here, the lower bandwidth is only equal to 1. There's only one non-zero subdiagonal. So then we have find W, or to denote by W the total bandwidth, or just plain bandwidth. and that is simply P plus Q plus 1. So in this example, it is equal to 4. But in general, it's P plus Q plus 1, where P is the upper bandwidth and Q is the lower bandwidth. So W is the total number of non-zero diagonals. The plus 1 is because upper bandwidth and lower bandwidth do not include the main diagonal. The total bandwidth does. So I have one subdiagonal, two superdiagonals, one main diagonal for a total of 4. Okay. So in general, the upper bandwidth is, as we non-negative, and it's at most n minus 1. You can have as many n minus 1 diagonals above the main diagonal. So this is for an n by n matrix. The lower bandwidth also between 0 and n minus 1. And therefore, W is, well, we always lump in the main diagonal. So this is at most 2n minus 1. I suppose that if a matrix is a 0 matrix, you could say it has bandwidth 0. That's not a very interesting case to discuss. So if the bandwidth of a matrix is less than the maximum possible, 2n minus 1, then we can say that the matrix is banded. But we're really interested in cases where the upper and lower bandwidth are particularly small. So a couple of examples of types of banded matrices of interest. When P and Q are both equal to 1, we call that tridiagonal. When P and Q are equal to 2, we call that pentadiagonal. There are 5 diagonals. So in this case, W is equal to 3 for tridiagonal. That's where the name comes from. And bandwidth is equal to 5 for the pentadiagonal case. And I've seen it written like if you have, for instance, upper and lower bandwidth equal to 3, so 7 diagonals in total, so we just call it a 7-diagonal matrix. Not necessarily a fancy term for that one. Okay. Now, as for why we talk about banded systems, these come up in application areas of interest. Tridiagonal matrices occur quite often in the numerical solution of PDEs, partial differential equations, or even some ordinary differential equations. And we'll see that toward the very end of the semester when we cover boundary value problems that a tridiagonal matrix is going to come up. Now, banded systems are quite interesting from a point of view of Gaussian elimination. So what I'm going to do now is examine that process of Gaussian elimination as applied to a banded matrix. All right. So I'll do a slightly different example. Let's write a few rows and columns. Okay. So here's a partial matrix. And I'm going to, for clarity, circle the start of the main diagonal. So here we have this, so we can see that we have a upper bandwidth, P, is equal to 3, and over here we have a lower bandwidth, Q, is equal to 2. So we had discussion in class about the work that needs to be done during Gaussian elimination on a banded matrix with clearly identifiable upper and lower bandwidth. So we're not going to go through that whole discussion again because there's nobody here but me. but I will give you the conclusions of that discussion in the form of a comparison between the general case of Gaussian elimination for a matrix where all the entries could conceivably be non-zero and a banded matrix. So we have general, okay, I'd seen that the recording had cut out, dang it. Fortunately, hardly anything had been missed. I saw that when it cut out, I just started to make this chart of the work done in Gaussian elimination for a general n by n matrix where any of the entries can be non-zero versus a banded matrix where non-zero entries are limited to this band. Okay, so if you think of what's done in column, I'll abbreviate call for column 1, column 2, down to column n minus 1 because you're working on only n minus 1 columns to eliminate entries. Because in the last column, there are no subdiagonal entries to eliminate. So in terms of how many entries to eliminate, we have n minus 1 entries to eliminate in the first column. Everything below that 1, 1 entry, the diagonal entry. Then you move to the next column, you have n minus 2, and it keeps decreasing all the way down to 1. So the total number of row operations, so that's what we're counting here. The number of row operations performed is just going to be the sum of all of these, the sum of all the numbers from 1 to n minus 1. And that is n times n minus 1 over 2. So order n squared, the big O of n squared row operations are needed. But what about for a banded matrix? Well, in each column, you only have a number of entries to eliminate, so 2 in this case. It's equal to the lower bandwidth, whatever that may be. So there's only q row operations for every column. Well, it may be less as you get down towards the end. So in column n minus 1, there's only going to be at most 1 entry to eliminate regardless. So it's on the order of n times q row operations that need to be performed. So notice n versus n squared. So we've saved an order of magnitude of work already. But then we look at each row operation, how many entries of that row are affected by row operation. So here in this case, every time we perform a row operation dealing with a first column, we're not touching a first column, but we touch all other columns. So n minus 1 entries per row, and then n minus 2, and so forth. So because we're performing order n squared row operations, each of which can affect nearly n up to as many as n minus 1 entries, so the total work is 2/3 n cubed plus some additional terms. But so order n cubed work has to be done in a general case. But what about row operations here? So for example, suppose I'm working on this row. I'm taking a multiple of the first row and subtracting it from the second. How many entries in this row are going to be affected? Well, this entry we just zero out. We don't do anything to it, so we don't count that. But in this row, there are 4 entries left. So you might think, oh, that's how many entries are affected by a row operation. But actually, it's 3, the upper bandwidth. And the reason why is this entry is 0. So this entry here is not affected. This value does not change. It's just these 3 entries, a diagonal entry, and then p minus 1 entries more. So a total of p entries per row. So it affects, so each row operation affects p entries. So we have n times q row operations affecting up to p entries each. So the total work is order n times p times q. So suppose p and q are both equal to 1 for a tridiagonal matrix. Then the amount of work is only order n. So we've shaved off 2 orders of magnitude for Gaussian elimination compared to the general case. So So that's huge. And what can be seen is if you look at the process of back substitution and forward substitution, that those are order n squared work, and in the general case are also only order n in the banded case. So why this is a big deal? If we consider some fundamental operations, matrix vector multiplication is one operation, and then the other operation is solving AX equals B. All right. Sorry about that. Okay. Now, for again, general versus banded. Okay. So for solving AX equals B, that I've just gone over. So we have order n cubed work in the general case versus order n work for the banded case. What about matrix vector multiplication? Well, what are you doing in matrix vector multiplication? You give an n by n matrix times the n vector. So I'll draw that situation up here. And the result is an n vector. You're going across each row and down each column. You multiply, 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 and you add them all up. And that gives you one element of a result. So to get each element of a result, you're doing n multiplications and n minus 1 additions, so order n operations, to get 1. But you have to get n of them all together. So the total amount of work for matrix vector multiplication is order n squared. Now, what about the banded case? You still have n elements to compute in your result, but for each one, you're only multiplying with a number of entries that's bounded by your total bandwidth. So what ends up happening is you get only order n. So if W is a total, if W is a total bandwidth, then you have only order n. Sorry, I can be more specific than that. If your total bandwidth is W, then the total number of multiplications you perform as you go across each row and down the vector is W. So in other words, I could be more specific here. I could say order W times n arithmetic operations. But the real point I want to make is, if we forget about any constants like P, Q, or W, for orders of magnitude of n, or for n by n matrix, because for a general case, matrix vector multiplication is much cheaper than solving a system of equations. So we try to avoid this situation. We prefer methods that involve matrix vector multiplication. But when you're dealing with banded matrix, the whole calculus changes, because now these two operations have the same order of complexity. Matrix vector multiplication is still a little bit cheaper. In other words, a constant in front of the n is smaller. But you no longer have that gap in terms of order of magnitude of work. So solving systems in the banded case suddenly becomes much more practical. It's on a par with this other operation that before was seen as being much cheaper. So the way you think about algorithm design is now fundamentally different for banded case versus the general case. Okay. Sorry, I was trying to remember what I did during class. Okay. So now what I'm going to do is examine more closely the algorithm for Gaussian elimination, starting from a general case and then stripping it down to what happens in the banded case. So you can see how much the algorithm simplifies. Well, actually, we're going to get more specific, not just the banded case. We're going to focus on the tri-diagonal case. That's particular importance anyway. Okay. Well, this video is going to be a whole lot shorter than the 75 minutes it would normally be. been a lot of class participation. Okay. All right, so here's the algorithm for Gaussian elimination. And I'm going to start with general case and strip it down to the tridiagonal case. So in that case, P and Q, the upper and lower bandwidth respectively, are equal to 1. All right, so the algorithm is looping over all the columns, and then looping over the rows below the diagonal, the computer multiplier. Unlike in class, I'm going to refer to the multiplier as Lij. I used to call it Mij, but I'm calling it Lij because that goes in the ij entry of a matrix L for the LU decomposition. So that would be Aij over Ajj. And then we have a lever loop that goes from j plus 1 up to n. And we have a main step of Gaussian elimination where we update the entry Aik. And then we end all these loops. I'm not going to bother updating B in this case. We're just focusing on matrix A for the LU decomposition. Okay, now, first, for a tridiagonal matrix, your lower bandwidth is 1. That means that you only have one entry below the diagonal within each column to eliminate. So we don't actually need a loop here. So I'm just going to cross that out. Instead, we just have one iteration, if you will. I is equal to n plus 1. Sorry, that's wrong. I is equal to j plus 1. So the first value here that it assumes in the loop is the only value it assumes. That means I can, where we see I here, I can replace it with j plus 1. Okay. And down here as well. Well, I'll cut it again. Hopefully I can get through the rest of this before it cuts out one time. Dang it. So what I've done when it cut out was updated I stricken this loop and said I equal to j plus 1 throughout. Now, as I was saying when it cut out again, this loop is also unnecessary because, as discussed earlier, the number of entries per row that are affected by row operation is equal to the upper bandwidth, P, which is only equal to 1 in this case. So we don't need an actual loop, we just do this one time. And again, k is only equal to the first value in the list, j plus 1. So now so I've removed this loop, and I can set k equal to j plus 1 throughout this line. And that's it. Now that's the whole algorithm. So now I'm just going to go ahead and erase all these ones. Then you can see more easily how simple the algorithm for Gaussian elimination becomes in the tridiagonal case. In upper bandwidth cases, there's still loops, but they only run a few iterations, like P or Q. So that's it. That's the whole algorithm. So we only have. It's getting aggy. Okay. So. But I remember what I was saying exactly as a cutoff. There's only 3n minus 3 arithmetic operations required by this algorithm because it's 3 arithmetic operations per column and minus 1 columns. Okay, But now, another improvement that needs to be made to this algorithm is we cut out all these floating point computations, but now we also have to cut down on storage. A matrix that's n by n is normally represented using a two-dimensional array that stores n squared entries. That's very wasteful for a tridiagonal matrix because you only have 3n minus 2 non-zero entries to store instead of n squared. So that's a huge difference if n is large. So for storage, we use vectors. So 3 of them. I use a vector A, which contains A1, A2 up to AN, which also holds the, in terms of the original matrix, is A11, A22 up to ANN. So that's the diagonal. Okay. Then I have a vector L, which contains only n minus 1 entries. And that corresponds to the entries A21, A32, all the entries below the diagonal. So that's, okay, subdiagonal. All right. And then vector U has U1, U2 up to UN minus 1. So now you see where there's 3n minus 2 entries in total. And that has the entries in the original matrix A12, A23, AN minus 1, N. That is the super diagonal. Okay. Now, notice how I do the indexing. So in the diagonal, the row and column indices are the same, so I just use that as the index. For the subdiagonal, I use the column index. That way I'm starting from 1. That says n minus 1 there. And then for the super diagonal, notice I'm using the row index, because that is starting from 1. Okay. So now, if I take my Gauss elimination algorithm, which I'll repeat down here in a more condensed form, okay, so we have Lj plus 1, j is equal to A, j plus 1, j over A, jj. And then I have A, j plus 1, j plus 1 is equal to itself, minus L, j plus 1, j, A, j, j plus 1. Okay, so now I'm going to translate this, these are entries of the original matrix, into entries for the, of these vectors. So L, j plus 1, j, I use the column index, so I'm just going to call that Lj is equal to itself, that's the same location, divided by the jth diagonal entry, which is just AJ, so I can just erase an index for that one. And then for the main step, I'm updating a diagonal entry, we just erase an index, so it's AJ plus 1 is equal to itself, minus Lj plus 1j, that's the jth multiplier, so that would just be Lj. And then jj plus 1, that is a super diagonal entry, and for that I use the row index, so that's just AJ. So that's it. That's your Gauss elimination algorithm for a tridiagonal matrix using vector storage. And this is reproduced in the textbook. But now you can see where it comes from. And in the textbook, there are similar algorithms for forward and back substitution using this vector storage. Now, there's one dicey issue. I'm going to go ahead and erase this because it's already elsewhere on the board. What about this fundamental ingredient of Gaussian elimination, pivoting, which I have not talked about today? Because row interchanges for a banded matrix can destroy the sparsity of the matrix. Sparsity meaning how many entries are zero. So in other words, it causes what's known as fill-in. And by fill-in, I mean new non-zero entries outside the band. So that wreaks havoc with vector storage. You can't store the matrix in like W vectors, or W is the bandwidth, because they won't hold all the entries you get. But the thing is, pivoting can still be necessary because we need it to minimize propagation of round-off error. There's a reason given for doing pivoting in the first place, besides avoiding division by zero. What we do about this is modify these pivoting strategies like partial pivoting. Instead of requiring the multipliers to be less or equal to 1, as partial pivoting gives you, maybe still bound them, like maybe less or equal to 2 or 8 or something like that. And then try to find the row to swap with that limits the damage to sparsity. So that's one way around this. On Thursday, we'll see a category of matrices, banded matrices for which pivoting is unnecessary. So, and that'll be a case that's important in applications. So at least there's, it's not all bad. But yeah, this presents a significant problem. And you can try this yourself if you make up a banded matrix. Let's go ahead and perform a row swap. Well, actually, we have the example over here. So, like right here, suppose I want to swap row 1 with row 3. Then that would cause these two non-zero entries to appear up here, but a bandwidth by 2. So you can see there why the banded case. Okay, so in summary, we really help with the efficiency of Gaussian elimination in terms of arithmetic operations and storage. These were equal to 0. And the nice thing is that if you don't do pivoting, Gaussian elimination preserves whatever banded structure you have, and that that lower bandwidth is inherited by L, the upper bandwidth is inherited by U. But there's a cost to it in terms of accuracy, because if you're not able to pivot in the same way as before, then you're allowing more propagation of round-off error, there's not really much of a free lunch here in certain applications. Okay, so I believe I've pretty much reproduced everything from the lecture, just without all the crazy talk arising from class participation. So now I know what went wrong during class. I'll make sure that doesn't happen next time. So now it hasn't cut out again, so I'll stop it and get this dang thing uploaded.